Welcome to Lecture D, Unit 7 Bonding. Lecture D is on intermolecular forces, so the forces between molecules. Remember that molecules are made with covalent bonds. All right, so when we talk about molecule interactions or intermolecular forces, molecules are things that are made with covalent bonds and only covalent bonds. If you have an ionic particle, you are not going to talk about their intermolecular forces or the molecule attractions because they're not molecules. So molecules can be attracted to other molecules or to ions. And our first step is to decide what type of molecule we have. Molecules are going to come in two types, polar or nonpolar. Polar molecules are like magnets. They have two sides to them. Magnets have a north and south pole. Polar molecules are going to have a positive and negative side. Nonpolar molecules are more like marbles, neutral all the way around. And it has to do with the arrangements of the electrons when they make those covalent bonds. Remember, they're sharing their electrons in their orbitals. Dipoles is another way of saying a polar molecule. Dipoles because it has two ends, di2. You're looking for a line of asymmetry. Any one line of asymmetry will make it a dipole. So if I look at a water, and this is a model showing you the electron configuration. So hydrogen sharing his electrons over here with water. Here's oxygen's 4 valence electrons that he doesn't have to share. These two he's sharing, the ones with the hydrogen. If I split this in half lengthwise, it looks like it has symmetry. It has bilateral symmetry. So it's the same on either side. But if I were to cut this way, this side of my molecule, the hydrogens are sharing their electrons with oxygen. They're being shared. So there's still a total of 4 electrons over here, but they're being shared between the 3 different nucleuses. Over here you have 4 that aren't being shared at all. So this oxygen side of your water picks up a partial negative charge. The hydrogen side picks up a partial positive charge. When we put 2 polar molecules together, the negative side of one molecule is attracted to the positive side of the other, where they're holding together, clinging together like magnets. Okay, so they're just going to stick. You can break this bond. It's fluid. It's not a permanent bond there. It's just a force. That's why they don't call it a bond. But it does hold the particles together. This is going to give substances like water a lot of surface tension. Water can perform capillary action where it pulls itself up a tube because it has this strong dipole moment and is highly polar. If we look at binary compounds where we just have 2 elements, it's very easy to see if they are polar or not. You look at their electronegativities. Bromine has a higher electronegativity than hydrogen does. So that means the electrons are going to be with bromine more often than they are with hydrogen. So when we split this in half, it's not symmetrical. The hydrogen side with the lower electronegativity is positive. The bromine side with the higher electronegativity is negative. If you were to put a whole bunch of hydrogen bromides together, the hydrogen side of one molecule is going to face the bromine side of another molecule, and they will cling together. They're polar. This gives polar molecules higher melting points and higher boiling points than you would expect for the size of the molecule because there is this interaction where they're clinging together like static cling. You can have polar bonds but have it be a nonpolar molecule, so you have to be careful of that. So let's draw out methane, CH4. Each bond between the carbons and the hydrogens is polar, but if we draw this molecule out and we look for its symmetry, it has radial symmetry. If it has radial symmetry, it is nonpolar. Yes, the hydrogens are sharing their electrons with the carbon. The carbon has the higher electronegativity, so all of the electrons will be with the carbon more often, but that charge distribution becomes even all the way around the outside, and so the outside of this molecule, the part that interacts with other molecules, has the same kind of charge all the way around, so it's nonpolar, like a marble. If you put a bunch of methanes together, they do not cling to each other. Ammonia molecule, NH3, if we were to split this in half this way, the nitrogen side with his two unshared electrons up here, he has this unshared pair of electrons, picks up a partial negative charge, and the hydrogen side picks up a partial positive. When we use models in class, we'll look at this three-dimensionally, and you'll see that the hydrogens all sit on kind of the same plane, and the two extra electrons up at the top. This makes ammonia a polar molecule, and the negative sides will be attracted to the positive side. So this would be a polar molecule. All right, you're looking for symmetry. Any line, I put the lines in for my model here, any line of asymmetry makes it a polar molecule. Please memorize that water is a highly polar molecule. All of the cool things that water does is because it is a highly polar molecule. For its size, water has a very high melting point and boiling point because he's highly polar. Memorize that. Moving on, let's take a look at water. Water is probably the most important molecule that we have. It's the most important compound. It's the one they're going to use the most often for your example of polar or nonpolar molecules. So when we look at models, so this is a Bohr model of water, notice that hydrogen, the nucleuses are not to scale. Hydrogen is only made of one proton, one electron, and no neutrons. So when he has to share his electrons with oxygen, all you have is this proton. That is going to make water very polar because now your partial positive charge over here is greater than it would be if he had some inner electrons. This oxygen has not only extra electrons, but these two inner electrons shielding his nucleus. So when he has to share his electrons with hydrogen, he's not left without any electrons. He still has electrons left, and that gives him this nice partial negative charge. Water is highly polar, and it does this special type of intermolecular force that we call hydrogen bonding. Because hydrogen is so small, and he's special because he only has that one electron and no inner electrons, molecules made with hydrogen, if they're polar, tend to be stronger dipoles than polar molecules made with other elements. Now, the bigger the electronegativity difference is between the hydrogen and the other element, so if we go to table S and we look at electronegativities, hydrogen is 2.2, oxygen is 3.4, nitrogen is 3.0. The greater the difference is between the hydrogen and the other element, the stronger the hydrogen bonding is. So water is more polar than ammonia, and water will form stronger hydrogen bonds with other water molecules than ammonia makes with other ammonia molecules. So the bigger the difference is, the more polar the molecule and the stronger the hydrogen bonding will be. The strongest hydrogen bonding then is going to be in molecules of hydrogen fluoride, because we remember fluorine has an electronegativity difference of 0. One of the ways that you'll see this is in a test question. They like to use the halogens because they think you've memorized trends on the periodic table. Remember that electronegativities decrease as you go down the group. So the strongest hydrogen bonding would be seen in HF, and the weakest hydrogen bonding would be seen in HI. If they give you different molecules and they want to know which shows the strongest hydrogen bond, it's always the one with the highest electronegativity. Van der Waals forces are going to apply to only nonpolar molecules. Van der Waals forces, nonpolar, you're going to memorize that. Van der Waals forces for nonpolar. Nonpolar things that have radial symmetry, so pure iodine or methane or carbon tetrachloride. What's another one of their favorites? Any of the diatomic molecules, oxygen and nitrogen. Anything that's nonpolar. If it has radial symmetry, nonpolar, the force of attraction that they talk about between them are called van der Waals. Now there's no charge, so it's not like magnets, they're like marbles. So there's no reason when you look at them to think that they would stick together. But we can make liquid nitrogen. Carbon dioxide is a nonpolar molecule, and yet we can have solid dry ice. Iodine can be a solid. So carbon tetrachloride is a liquid. There's no charge difference here to explain why they cling together. They are not like magnets, they're like marbles. So van der Waals forces say that the bigger they are, we're talking about finding their gram formula mass. Pure oxygen has a gram formula mass of 32. Carbon dioxide is going to be, 32 and 12, 44. So we're talking about their gram formula mass. The higher the gram formula mass, the more likely you are to see it as a liquid or a solid. Carbon tetrachloride with each chlorine having a mass of 35 compared to methane where each hydrogen only has a mass of 1. Carbon tetrachloride is much more massive. At room temperature it's a liquid and methane is a gas. Decreasing distance between molecules. How do we decrease the distance between molecules? We increase the pressure and we decrease the temperature. So it's the same way where we talk about an ideal gas. How is it less ideal? It's less ideal when there's high pressure and low temperatures. It's more ideal when there's low pressures and high temperatures. Same thing happens with van der Waals. The reason it's less ideal when there's more pressure and the temperature is low is because these van der Waals forces help them start to cling together and they start to do things like turn into liquid. If you have liquid nitrogen and you have it in an open container, so you decrease the pressure, it immediately turns back to a gas. So memorize for van der Waals forces: size, increasing size, stronger. Decreasing distance, that means increasing pressure, stronger, and decreasing temperatures, stronger. One last intermolecular force to talk about are these molecule ion attraction. In order to have molecule ion attractions, you need molecules, so that means something made with covalent bonds, and ions, so that means something made with ionic bonds. So this is basically talking about what happens when we put ionic compounds with a polar solvent. What's our favorite polar solvent? Water. Okay, and that's why we have all of those solutions that are aqueous. So most of the chemicals that we work with are ionic compounds dissolved in water. They're almost all aqueous. When we put an ionic compound into water, water is polar enough that it can interact with the ions. So sodium chloride splits in half. Remember, we call this dissociation. It will dissociate your positive sodiums in this diagram down here. Those would be our red dots. Become surrounded by the water molecules, and in this diagram, the negative side of those little ovals would be your oxygen if we're talking water, and the positive side would be the hydrogens. The waters surround the sodium so that it can't touch chlorines, and the hydrogen side of the waters surround the chlorines so they can't touch sodiums, and it breaks the particles in half And that's why we get this dissociation where we write the compound out like so, so that you know there's charges. You're supposed to know when you see this ionic compound in an aqueous solution that it's really broken apart into its ions. The areas of charge allow it to conduct electricity. They will ask you to draw diagrams of this. They especially like to use water, and you just need to remember that the oxygen side of the water is your negative and the hydrogen side is your positive. This molecule ion attraction explains why ionic compounds can only dissolve in polar solvents. If you put them into a nonpolar solvent, there's no force of attraction greater than the attraction between the positive ion and the negative ion, so they stay hooked together and just stay solid particles. So an ionic compound will not dissolve in a nonpolar solvent, only in polar. When we use water as our solvent and they get surrounded by waters, they call it hydration. Remember how to draw these diagrams. So if I were drawing this on paper and I had to show the molecule ion interaction, I would draw something like this and show chlorine being faced by the hydrogen sides. And if I were picking this out in a multiple choice question and they gave me a list of substances and they say which one shows molecule ion interactions, well, this doesn't because all I have are ions. That's an ionic compound. This doesn't because all I have here is a molecule. But if they show you an ionic compound that's aqueous, here's my ionic, here is my polar molecule. Anytime you see an ionic compound aqueous, that is your molecule ion interaction. So in a multiple choice question, you are looking for an ionic compound with an AQ. And that wraps up intermolecular forces.